Okay, here we are, chapter 11, the third chapter in the unit. We started with chapter 9, rotational motion, then we did simple machines. Now we're doing universal gravitation and satellite motion. So a lot of this is going to harken back a lot to chapter 9 because we're going to talk about satellites going around in a circle. And we're going to talk about what keeps those satellites going in a circle, namely the force that does that, which is gravitation. So that's how we fit these two together in a single chapter. We're going to start with the gravitation side of things and move on to the satellite things later on in the chapter. So picture here on the front title slide of Isaac Newton, who we associate with gravity and with the idea of universal gravitation. There's the story of the apple falling from the tree. And really, people knew apples fell for many years before Newton, but he gave us some insights. So Newton was investigating universal gravitation in the 1680s, and he came up with a mathematical way of describing gravitation. And you see here this blue equation. Now, that wasn't quite what he had available to him, but it's what we call today universal gravitation. It's what a lot of this chapter is going to revolve around. It's a somewhat more complicated equation than some that we've covered. It's got 5 variables total. We've got 2 different masses and a distance and a big G, which is a constant, and then of course the force of gravity. And we've talked about the force of gravity already, but this is going to be a little bit of a different discussion. So about this, well, here, let's back up there for a moment. Yeah, so this is what's called an inverse square law. An inverse square law. Inverse, if we remember from mathematics, whether we have a variable or whether we have a number. If we want to take the inverse of that, we'd simply we divide by it instead of multiplying it. So the inverse of x is 1 over x. The inverse of 3 is 1 over 3. So 3 becomes a third, x becomes 1 over x. So that's what the inverse means, and then we're going to square it. We're going to square it. So you see, what we're really talking about is that force is an inverse square law with respect to distance. So it's going to be 1 over the distance, but it's actually 1 over the distance squared. So that's why we call it a square law. And this has a lot of practical implications. Newton understood that gravity worked this way. Many things in nature work this way. Here, for example, we have this being expressed in terms, it can be expressed in terms of light, right? So if you have a light source, as that light spreads out, this is probably the easiest way for us to think about it because we can see light more immediately than we can see gravity. As you move out, that light gets spread over a larger and larger area. And so it's the same energy, it's the same amount of light, but as we spread it over a larger area, each piece of that area gets less. And so that's what we talk about when we talk about the intensity of the light going down as 1 over d squared. We talk about the gravity force going down as 1 over d squared. You can think of it in terms of spray paint, right? If you take a bottle of spray paint and you spray, as that paint spreads out, it's going to produce a thinner and thinner covering of paint because it's got to be spread over a larger area. So anyway, this is a really important idea. Without understanding inverse square law, this whole chapter is a bit of a struggle. So there's a link here in the PowerPoint if you have access to the PowerPoint, and there's also a link in the description of this YouTube video. And I would encourage you to pause my video here for a moment and go watch this YouTube video. The man does a very excellent job of explaining inverse square law and then does some examples using Newton's universal gravitation, which is one of the applications, and that's the one that we're working with. So go watch that now, please. So in addition to being an inverse square law, gravity also depends directly on both of the masses. So what this tells us is that the force of gravity between any 2 objects in the universe, and this also tells us that any 2 objects in the universe will have a force of gravity between them. As long as the 2 objects have mass, they will attract one another. And that's a kind of a revolutionary idea, a lot easier to think about when we think about it in terms of astronomy. We understand that the sun and stars pull on the planets that are around them, and planets pull on the moons that are around them. But it's a little harder to take this idea and bring it back to Earth and to think about the fact that I have mass and a student sitting in the front row of my class has mass, and therefore we are attracted to one another according to Newton's law of gravity. But this is true, and the attraction is mutual, right? So you can switch M1 and M2, and you still get the force of attraction between the objects. So the Earth is pulling on the moon is also pulling on the Earth, and this is very real and has very real practical results. And this d, of course, is the distance between the objects. Now, again, we discussed back in chapter 7 the idea that if you have an object that has some size to it, we need to treat the mass of the object as being at the center, all the mass of the object as being at the center of the object. So this distance is measuring between the center of mass of the two objects in consideration. So we understand what that's going to mean algebraically, right? I mean, because we can think about, well, if I'm measuring the force of attraction between me and my bed, and I go and lay on my bed, doesn't that mean the distance between me and my bed is 0? And so if we divide by 0, we're going to get an explosively large force. Well, no, that's not really true, because even when I'm laying on my bed, the distance between my center of mass and the center of mass of the bed is non-zero, and so the force of attraction between us is still going to be actually quite a small number. And the reason that number ends up being so small is because of this constant here, right? And we commonly refer to this as big G. And the reason we do that is because, we have a lowercase g, right? The one over here, that means something else that we learned about way back in chapter 5 when we first introduced the concept of gravity. And so we want to keep these two constants very distinct and separate because they have very different values and they have different meanings. So we call this one little g, and we call this one big G, and we always capitalize this one to show that it's that particular constant. But obviously 9.8 is a significantly different number than the value for large G, which is 6.67 times 10 to the negative 11. 6.67 times 10 to the negative 11. That's a very, very, very small number. We understand exponents. We understand exponents are telling us how many powers of 10 we would need to multiply by. So if we just wanted to multiply this number by 10, it would be times 10 to the first. And at times 10 would, of course, move the decimal place over. It would turn our 6 into a 66 and would make our number larger. But when we have a negative exponent, it's really about how many powers of 10 we're going to divide by instead of multiply by. So here we're going to take 6.67 and we're going to divide by 10 11 times. And that's going to result in a number with a tremendous number of zeros before we get to the 6. In fact, this represents 6 parts of 100th of a billionth. So that's an incredibly, incredibly tiny number if you want to think about it in terms of fraction. 6 parts out of 100, but that's 6 parts out of 100 of 1 piece out of a billion. It's incredibly, incredibly tiny number. And that is why when we go to calculate the force of gravity between any normal size objects, say again, me and the student in the first row, we stick our masses in. Even if we had large masses, we stick our masses in, we'd stick a reasonably small distance between us, and then we divide by a billion, actually divided by more than a billion. And so the force we get out is really, really, really tiny. And this force really ends up being unmeasurably small for anything except for when we get masses that are so large that they're expressed with an exponent that starts to rival this, but in the positive, not negative direction. Things like planets and moons and stars that have big masses, very, very large masses. So you might wonder, where did we get this number? Where did we get this tiny, tiny number from? And the answer is Newton never got there. He never got there. We're going to talk about who came up with this number and how they did it on the next slide. But what we have found is that this number is universal. It's as far as we can tell, universal all across the universe. This large G constant appears to be the thing ruling and present in this equation. And we can look across the universe with our telescope, see stars, planets, galaxies in other parts of the universe, and we see how they interact with each other, and they interact via gravity, right? There's lots of rotation, lots of orbiting going on in a galaxy halfway across the universe. And from all that we can tell, it is being governed by this same equation with this same constant. But Newton didn't have that constant available to him. He had not been able to measure it. He knew the force was directly proportional to the masses, product of the masses, and inversely proportional to the square of the distances. But he didn't have the blue equation. He had this yellow equation because he didn't have this constant. He had an idea that there would be a constant, but he did not have that value. So you can still learn a lot from this yellow equation. In fact, if you go back and think about the inverse square law video you just watched on the on this slide, actually, you will see that even if you had this yellow expression instead of the blue expression, you could have done everything that he did in that video and gotten the same results. The last thing I want to say on this slide is about the units here of big G. It's got very strange units. I mean, familiar pieces that we're familiar with, but an odd combination. Newton meters squared in the numerator and kilograms squared in the denominator. But these units were carefully chosen for our benefit, because when we stick this into this larger equation, right, we're going to end up with a mass in kilograms times a mass in kilograms. Well, kilograms times kilograms is going to give us kilograms squared in the numerator. And then if you put that together with the units of big G, now we've got kilograms squared in the denominator. So we can take the kilograms from our masses and we can cancel them out with the kilograms from our constant. And the same thing with the meters, right? We're going to have some distance, which we need to put in meters, and then we're going to square it. We're going to square the number, we're going to square the units. So we're going to end up with meters squared in the denominator from that inverse square of the distance. And so the meters squared will cancel, the kilograms squared will cancel, and all that we'll have left is newtons, which is exactly what we want, right? Forces are measured in newtons. So these units were actually very, very advantageously chosen, and the constant was chosen to be expressed in these newtons, or in these units, for our convenience. But just the thing that we need to remember then is that our mass always needs to go in kilograms, because otherwise the units will not be correct. Therefore, the constant being used is not correct. And that's usually not an issue. Usually we in physics express our masses in kilograms. Chemistry people think in grams. We think in kilograms. But the bigger risk is going to be in the distance, right? The tendency we might have to put in a very large distance in kilometers instead of in meters. And that can be a real problem, right? Because if we're supposed to be putting it in meters, we put it in kilometers, well, we're off by a factor of 1,000. And then we square the fact that we're off by a factor of 1,000, and now we're actually off by a factor of 1,000,000. And being off by 1,000,000 is a big deal. So it's very important that we remember to put our distance in meters. And you might say, well, what if I want to put it in kilometers? What do I need to do? Well, then you need to get a whole different value for big G. And I don't know any other units, any other values for big G. That you could do it, you could convert it into other units, but it's better to just to work with it in this way. So who was the guy who came up with big G? And I'm not a big date person, and I'm not going to require you to remember these dates for the exam or anything. I just want to drive home the difference here. Wow. Newton was in the 1680s and Cavendish in 1797. So we're talking 100 years. For 100 years, physicists had some degree of understanding of the fact that there was this constant out there that they did not know and that they could not measure, and they made efforts in that direction for a long time without a lot of success. And again, Newton would be what we would consider a theoretical physicist. He came up with this formula, this way of expressing mathematically the size of the force that we would expect, and showing what variables it was going to depend on. And then you would have Cavendish, who did a lot of other things as well in the realms of chemistry and in physics. But one of the things he did was create this very complex and useful experiment to get a value for big G, which was a very, very tiny number. So, but he wasn't even interested in it for big G's sake. He was interested in what he could figure out once he had the value of big G. His goal was to weigh the Earth, to find out what the mass or weight of the Earth was. And that was something that was a very interesting question, right? There were a lot of questions out there about what the Earth was made of. We understood the Earth was very large. We understood that the Earth was a sphere, but what was inside? There's actually quite a bit of interesting science fiction about the Earth being hollow, and that if you went down the right volcano, you could get inside the Earth. Um, and you know, a lot of science fiction is based on scientific ideas at the time, and the best science fiction is plausible, at least. And since they didn't really know what the mass of the Earth was, they they couldn't really definitively say for sure whether it was hollow or not. And so Cavendish wanted to find out what the mass of the Earth was. And you know, this is at the end an algebra equation, right? So you can solve for an unknown, say the mass of the Earth, if you know everything else. So take the classic example, right? The apple falling from the tree. We can express the mass of the apple. We can express the weight of the apple. We can measure the distance from the apple to the center of the Earth, right? The apple's essentially on the surface, and so the distance from the apple to the center of the Earth would be the radius of the Earth. And we had good numbers. We've had good numbers for the radius of the Earth for a very long time. That was not the issue. So we'd have a mass, we'd have a weight, and we'd have a distance, and we would want to know the other mass. But the problem is we don't know what big G is. So now we have two unknowns and one equation, two unknowns. You can't solve that. And you might think, okay, well, that's fine. What if I could find big G with some other equation? You know, what if I do the apple and me, right? I know the apple's mass and I know my mass and I know the distance between us. But the problem with that approach is what's the force of attraction between the apple and me, right? We know now, because we understand the value of big G, the force between me and the apple would be, you know, a millionth, maybe a 10 millionth of a newton of force, but we can't measure something that tiny. So we're still stuck with two unknowns, whether we use the Earth and something else whose weight we would then know, or whether we use, but we wouldn't know the mass of the Earth, or we use two objects whose masses we know, we then wouldn't be able to measure the force between them. So we had this issue. Now, Cavendish's approach was to use two small objects, figure out the force between them, then he could solve for big G. And once he had big G, then he could go back and find the mass of the Earth, which is what he was interested in. So he did this with a very complex apparatus. Here's a picture of what he attempted to do. He had this built inside of a room, inside of a box. Air currents are extremely detrimental. You can go on YouTube and find a lot of videos of people trying to recreate this, and it's really, really hard to do. This is a video of a young lady, a high school student, trying to recreate this experiment, and she does a very, very good job considering the materials she has to work with. She goes into quite a bit of detail of how to actually wrangle the mathematics to do the calculation, and that's not something you need to know for this class, but if you're interested, you of course could try to follow her mathematics. But the bottom line was that he had to measure this extremely tiny force of attraction between known masses. So he had two masses on a rod that were hanging from a wire or a string, and then he had two larger masses that he would bring near those masses so that there would be an attraction, and he'd have one on each side so that both, right, in this case, they would both be trying to create a counterclockwise rotation, right? This one's trying to be pulled up on the right and down on the left, and that's going to create a counterclockwise rotation. Now, the amount of movement is going to just be absolutely tiny, right? But if you have a mirror on the wire or the string and you shine a light on that mirror, even the slightest change of angle will show up with the light spot on some distance scale. Again, because as we've kind of talked in chapter 9 about circular motion and how, you know, theta is theta, but if you take theta and you multiply it by the radius, then you get the arc length. So even if theta is really tiny, if you can make the radius large enough, then you start getting an arc length that is measurable. And it goes into the torque on the string. And again, this extremely tiny force, but with the proper mathematics, you can measure that tiny force on the string and get a value. And Cavendish was able to do it, and his answer was within 1% of the modern value, which is just incredible for the 1790s. But he was able to do it, and this provided great support for us to be able to take Newton's principle of force dependent directly on the product of the masses and inversely on the square of the distance and actually turn it into a true equation with an equal sign that would allow us to begin to make calculations, particularly in the astronomy realm. And like I said, with big G and the mass of any object, he was then able to ascertain the Earth's mass. And then with the Earth's volume, you could ascertain mass divided by volume, get the density of the Earth, and find that that was not significantly different from the density of most dirt and rocks and that sort of thing, which convinced us that the Earth was in fact solid all the way through, which is still our belief today. So big G was determined by Cavendish, but in science, we of course, once we have discovered or measured something, we want to measure it again. First of all, we would repeat the original experiment to make sure we're getting the similar results. But then to try to find a different experiment, slightly different, that would measure the same thing to make sure there's not something inherent in the experiment we were doing that was causing error of some kind. So Philip von Jolly, once he had a value for big G, he set up a balance that looked like this. Had it all balanced and then rolled this boulder in. And when he rolls the boulder in, the extra force of attraction of the boulder is going to undo his balance. And then if he can add just the right fraction of an ounce on the right side, he can re-achieve balance and then associate that amount of added force with the particular part of gravity that comes from the boulder. This would have been an incredibly difficult and monotonous process to attempt if you didn't have some idea of the value in the first place. So this is a great confirmation experiment, would not have been a great initial experiment, which is why Cavendish is the name we know and not this guy, even though this guy's name is more fun to say. So a couple of check questions, a couple of practice questions, and this goes back a little bit to how he was explaining things with the inverse square law. You know, we have this big equation, and you'll have some homework problems, you'll have some quiz problems in which you're asked to plug all of the numbers in, and we know big G, 6.67 times 10 to the negative 11th. It's scientific notation, and if you want to plug in the mass of the Earth, that's going to be scientific notation too. So, and we'll do some of those a little later in the PowerPoint, but all that scientific notation being plugged in is a lot of algebra and a lot of computation and a lot of having to be very careful about how we put it into our calculator. And that kind of takes away from the focus of the physics principle, which is that force is directly proportional to the product of the masses and inversely with the square of the distance. So what we can do is what I call factor questions, which is what he did in the inverse square law video, in which we want to know how much does the original answer change. We don't care whether this answer is 17 million newtons or 7 newtons. We just want to know how much will it change if we adjust our inputs by a little bit. So here's the question, the first question. How much is the gravitational force between a pair of planets going to be altered if the mass of one planet doubles? So obviously the force of gravitation between planets is going to be a large number. But if one of the planets was twice as big, how would that affect the force between them? And then what if we doubled both the masses instead? So we do this by a factor, right? We don't actually have any numbers to plug in. What we have to plug in is the number 2, right? 2. If we put a 2 in next to one of the masses, how does that change everything? Well, we understand that the laws of algebra, that multiplication is commutative and that we can factor the 2 out, right? So if we took the 2 out, here, now it's not there anymore. Now we've got big G, M1, M2 all over G squared. In other words, we have exactly what we started with originally, just all of that times 2. So that means we can take our original answer, right, which is what all of that was equal to, was our original force answer, and we can multiply it by 2, and that's going to be our answer. If we would double the mass of one planet, that would increase our answer by a factor of 2, which might seem a little elementary, but as we do some more, you'll see it's not always quite that simple. So what if we double both of the masses? Well, then we put in a 2 here, and we put in another 2 here. So now we've got 2 2's, and we factor them both out. We get 2 times 2. And so instead of having a 2 out here, we'd have a 4 out here. And so we have 4 times the original force if we double both of the masses. And you can go on to different combinations, right? What if we tripled one mass, but only had half as much for the other mass? Well, then we'd have a factor of 3 and a factor of 1/2, and that would give us 3/2. So you simply do multiply the factors on the masses together, and that's how much our force is affected. But what would happen if we instead we're messing with the distance, right? It's an inverse square law. So it's inverse. We're dividing by the distance, and we're squaring the distance. So what if the planets, they've gone back to their original masses now, what if they're twice as far apart? Twice as far apart. So we have this expression, and we put in 2d instead of d. What is that going to look like? So a lot of people say, oh, well, it should be 1/2, right? Because we have a factor of 2 down here in the denominator, so 1/2 is 1/2. Well, it's actually not quite 1/2. It's not 1/2 because we need to square our distance. We need to square our distance. Oops, this didn't get put up in the, you know, we're supposed to be squaring that. So we got to square the distance. So if we square the distance, we also have to square the number with the distance, the factor with the distance. So when we do 2 squared, we get 4 in the denominator. So we end up with 1/4 of the original force. And if they were three times as far apart, then we would be squaring 3 instead of squaring 2. So it would be 1/9. Okay, and you can imagine a situation where we would have both of these put together, right? What if we have 2 times one mass and 2 times the other mass and 3 times the distance? Well, then we have 2 times 2, which is 4, divided by 9. We would have a factor of 4/9. Okay, and all this math is much easier for us to do than to actually plug all the scientific notation into the actual problem. So again, hopefully that makes sense. If not, rewatch this part of the video or go back and rewatch the inverse square video that the other guy showed, because this is an important idea and an important way to check your understanding of what's going on in this equation. So everything pulls on everything else. We talked about this already. All masses pull on everything else. And so this gets very interesting in real life when you have a bunch of significant masses near one another. For example, in our solar system, where we have 8 different planets going around the sun, plus a whole belt of asteroids, plus a Kuiper belt further out of more asteroid-type material, it becomes quite interesting, right? It's very simple to think of nothing but the Earth and the sun, and so the sun goes around the Earth. The Earth goes around the sun. But when you've got a bunch of other planets pulling too, it makes for a little bit of confusion and complication. So when you actually look at the orbit of, say, a planet like Mars, who's got us inside of it and Jupiter outside of it and a whole asteroid belt, it's not quite as pretty as a perfect circle. And so we call them perturbations when the planet is orbit is disturbed away from what is normal. We call it a perturbation. And so, you know, way back in the day, before we had seen all of the planets, we had 7 planets, and the furthest out was called Uranus, and it was the furthest out, and it had been going around the sun. We've been tracking it as it went around the sun for a number of years now, and we noticed some of these disturbances, right? But we noticed them before. We'd noticed them even with Uranus before, right? Because Jupiter's the biggest planet in the solar system. It has the biggest mass, and so it has the biggest pull. And we'd seen how Uranus was disturbed or perturbated when it went past Jupiter, and likewise Saturn, which is even closer to Uranus and further out, so therefore closer to Uranus. But we noticed that Uranus was doing some weird stuff even when Saturn and Jupiter were on the other side of the sun, too far away to be causing this problem. And so there was a lot of, there was some people who were sitting at home studying this orbit, not at home, scientists who were studying this orbit, and they found that these perturbations could be explained mathematically if there was another planet even further out than Uranus. It was explained by Uranus potentially, you know, having a planet further out pulling outward on Uranus, and that would account for this red path it was following instead of the black path, which we would expect it to follow. And so there were actually 2 men who did this. And John Adam had the disadvantage of sending his information to an astronomer who didn't believe him and didn't check. And Leverrier had the advantage of sending it to somebody at a different observatory who said, hey, well, might as well look. If he thinks there's a planet in this part of the sky, I'll take a look. And they discovered the fourth planet from the sun, namely Neptune. And that's how Neptune was discovered. And it turns out, as they went back and looked at previous pictures they had taken, they had actually seen Neptune before. They had not realized that they were looking at a planet. It's a very dim planet, and can be mistaken for a distant star. But that's how Neptune was found, and actually later that's how Pluto was found. And then later on they determined Pluto actually wasn't big enough to be causing the further perturbations that they were observing, and eventually Pluto got demoted. But that's a whole nother story. This is how Neptune was found, because of the perturbations of Uranus, which come directly from the fact that everything pulls on everything else, and universal gravitation. So when we talk about here on the Earth, right, the weight of something on the Earth, we've been talking about that since chapter 5, and we have not needed this big, massive equation that I just taught you this chapter. So why is that, right? We talked about the idea that weight was equal to your gravity force, and your gravity force is equal to this big expression, which if you're on the surface of the Earth, it's going to be big G, which is universal, whole universe, little m, or m1, which is your mass, or the apple's mass, or whatever's the rock's mass, whatever we want to find the weight of. This is the mass of the object whose weight we're trying to find. We also need the mass of the Earth, right? Because the Earth is what is applying a large gravitational force to us when we're on the Earth, right? We're on the surface of the Earth. It is pulling on us. That's what holds us to the surface. That is the dominant gravitational force around us. So we need our mass, the mass of the Earth, and then the distance between us and the Earth. And again, the radius of the Earth is something like 6,300 kilometers. So whether you're sitting on the ground at sea level, or whether you're even on top of a mountain that's maybe a couple of kilometers high, that really doesn't change much in terms of the radius of the Earth being 6,300 kilometers. So we just call it the radius of the Earth if you're anywhere on the surface of the Earth. Would it be slightly less if you're on top of Mount Everest? Yes. Would it be slightly more if you're in Death Valley? Yes, but not enough to change the number that much for us. So, but if we're on the surface of the Earth, as this bullet point here tells us, of the 4 variables, 3 of them don't change. Big G doesn't change anywhere in the universe. As long as we're on the Earth, the mass of the Earth is not going to change. The radius of the Earth is not going to change. Only one thing's going to change, right? We replace the mass of the apple with the mass of the rock. We replace the mass of the rock with the mass of you. We go around and make those adjustments, but these 3 variables are not changing. So if we were lazy, I mean, if we were efficient, we would replace these 3 variables with a single variable, which would be equal to the value of those 3 put together. So M1 is still changing, but we take these other 3 that aren't changing and we put them together and we'd call them something. And since it's associated with gravity, maybe we'd call it little g to represent that value. And so when you stick those numbers in, and again, test this, put this into your calculator, show yourself, convince yourself this is true. This is the value for big G, 6.67 times 10 to the negative 11th. The mass of the Earth, 5.97 times 10 to the 24 kilograms. There's a great chart with the mass of all the planets in chapter 11. Just start flipping through the pages. You'll find it. It has the mass of every planet. It has the radius of every planet. Here's the radius of the Earth from that chapter. And what you get, 9.78, which is approximately 9.8. I think they rounded the Earth's radius slightly. Usually we say the official value is 9.81, but that's not important. The point is, you put those 3 numbers together, and as long as you stay on the surface of the Earth, you're always going to get 9.8. And that's why I taught you this equation back in chapter 5. That's why we can use this equation. This equation is valid as long as you remember what the restrictions are. We have to be on the surface of the Earth. And we're going to talk here momentarily about satellites that are up above the surface enough that this is not the approach that we take. But if we're on the surface of the Earth, we can use this. We don't have to use the universal equation. So again, here's an example of why that equation can't always be used, right? So if we're on the surface of the Earth, we have some object, it has a weight of 100 pounds, that's great, okay? But if we go twice the radius of the, or if we go one radius of the Earth above the surface, right, a height of one radius, which would actually be a distance from the center of the Earth of two radiuses, right? This is another factor problem. Right? We stick a 2 down here, we square the 2, we get a 4. So now we have 1/4 of the original force. A 100-pound object has dropped down to being only 25 pounds. And again, at 3R, it's only 11 pounds. And you go out and you can see how they're doing this, right? They keep squaring the factor that we have, and that keeps reducing our force by a significant amount. So we got to be on the surface or very close to the surface in order to use that shortcut equation, F equals mg. So what was it that Newton really did, right? He didn't discover that apples fall off of trees for the first time. People had known that before. What did Newton really discover? What did he really explain to us? And it's hard for us to fathom some of the things, historical perspectives that people had, because we move past that perspective and we understand things better today. But a big part of the reason why there are two fields of science, right? We call astronomy the study of space, and we call physics the study of stuff on the Earth. A big reason why there are two different fields is because for many, many years, they believed the laws of physics were different in the sky than they were on the Earth. And again, that's because they looked up into the sky and they saw the sun going in a circle, the moon going in a circle, the stars going in a circle, the planets going in. So they saw everything going in circles up there. And down here, we don't see very many things going in circles at all. And so the idea was that there must be different laws of physics. Somehow up there, everything goes in circles, and down here, everything does not. And this is that critical moment that Newton is able to show people that no, the laws really aren't different. The laws are the same. Astronomy and physics on Earth are ruled by the same laws, the same principles. And so he did that by showing that the moon, something clearly from astronomy, and the apple, something clearly here on Earth, were doing the same thing. We're doing the same thing. Now that's hard for us to wrap our heads around initially, right? Apples fall straight down, right? Apple straight down hits the ground. That's a straight line, right? And the moon, it's going around the Earth, right? It's a circle versus straight line. So how are you saying these are the same thing, Newton? What's the deal? And he explained it with something that we call Newton's mountain, and there's a picture of it right here. And it's a pretty a brilliant way of explaining it, because it really can make a lot of sense very quickly. He says, imagine you have a mountain and it's very, very tall, and we have to get above the air, right? If we have too much air, we have air resistance, it's going to goof everything up. So we've got a big mountain to get up above the atmosphere. And at the top of the mountain, we shoot cannonballs sideways, right? We shoot cannonballs sideways. The cannons shoot cannonballs. So we're way up on this mountain. And well, first, imagine we don't shoot the cannon. Imagine we just let the cannonball roll out of the cannon's barrel. It's then going to fall straight down, right? Just like the apple, the cannonball is going to fall straight down, okay? But if we give it some gunpowder and we shoot it, then it will move forward and fall. And so it will follow a projectile and a trajectory of a projectile, which we're familiar with, right? We've thrown baseballs, we've shot cannonballs before, we understand. It's going to fall to the Earth. It's going to make some progress, but it's going to fall to the Earth. And if we shoot it faster, it'll go a little further, but it will still fall to the Earth. Well, he shows you with this Newton's cannon that if you could just keep increasing the velocity without actually exploding your barrel and killing yourself, if you could keep increasing the velocity, eventually your cannonball would make it further and further around the world before it fell to the surface. And if you could shoot it just the right speed, just fast enough, then the curvature of the cannonball's fall would match the curvature of the Earth. Which means if your mountain was 200 kilometers above the surface, your cannonball would stay 200 kilometers above the surface the whole time, because by the time it fell, the Earth would have moved away, right? If the Earth was flat, the Earth is not flat. If you've got any flat Earth friends, ask them to explain Newton's cannon to you. If the Earth was flat, this cannonball would fall and it would strike the Earth, right? But because we are shooting the cannonball so incredibly fast, and because the Earth is not flat, by the time the cannonball reaches this point, the Earth is down here, and we've got some big height above the surface again. And you keep doing that as it falls all the way. I mean, down here it's falling up, right? Because it's being pulled toward the center of the Earth. This is gravitational force pulling it toward the center of the Earth. That's why things fall, because gravity pulls us toward the center of the Earth. But if we shoot the cannonball fast enough sideways, it never hits the Earth because it's moving so fast sideways that by the time it would have hit the Earth has curved away and is not underneath it in the same way anymore. And of course, if we shoot it too fast, then the distance from the Earth will be increasing, and eventually it will spiral out and it will escape and fly off into space. If we shoot it just a little bit too slow, it will slowly spiral until it catches the atmosphere, and that's the origin of the phrase death spiral, because you're slowly coming in and you're going to eventually end up hitting the ground at a very high speed. So suddenly we've gone from the cannonball being like the apple falling straight down out of the cannon's barrel to the cannonball being like the moon. This is what the moon does. The moon falls around the Earth indefinitely, right? And the cannonball comes around, if it would run and smack you in the back of the head, which would be very bad. If you got your cannoning yourself off the mountain, though, the cannonball would go right over where the cannon was, and it would do it again and again and again and again. And it doesn't need any more boost. It doesn't need any more gunpowder. It doesn't need any rockets. It's just going to fall around the Earth, powered by gravity, trying to fall into the Earth, but moving sideways always too fast to actually fall into the Earth. And this is what the moon does, and this is what all our artificial satellites do. And it's really quite incredible that they get up there and they stay going around without any boost or help from us. So again, here's a video, a link in the description to this same video about Newton's cannon, where they'll just show you this with some other animations and talk about it a little bit more, just to try to drive home the idea of Newton's cannon and how it connects the apple to the moon and shows that gravity is what runs astronomy, and gravity is also what runs things here on Earth. So satellite motion. So what is going on when you have a satellite, something that is orbiting another object, in this case, something that's orbiting the Earth? The moon does it, and artificial man-made satellites do it too. We're going to talk about an artificial man-made satellite in something called low Earth orbit, which is only about 200 kilometers above the surface. The atmosphere goes up about 100 kilometers, so if you're 200 kilometers, you're good and safely above the majority of the atmosphere. So what we're going to do is we're going to say, look, it's going in a circle, right? This is chapter 9. If you're going to go in a circle, you got to have a force toward the center, a centripetal force pulling you toward the center, and that force is supplied on a satellite by none other than gravity, right? Gravity. So we're going to take our centripetal force equation, we're going to set it equal to our gravity equation, and we're going to see how we can solve for the velocity of the satellite. Now, initially we go, oh, well, that one's got 3 variables. That one's got 4 variables. This is going to be ugly. But you will notice that a bunch of these are overlapping variables, right? This is the mass of the satellite, right? Bigger the object, the more force we need to make it go in a circle. This is the mass of the satellite. So he shows up on both sides. So he also will cancel out when we set the two of them equal to each other. And then we have the radius, which shows up on both sides, and on this side it's squared, on this side it's not, so it's not going to totally disappear, but it's going to partially disappear. So when we do that, we find ourselves with V equals the square root of G, mass of Earth, divided by the radius, because again, M1 dropped, this R came over here and eliminated one of the R's in the denominator, and then all we had left here was V squared, so we just take the square root of everything that's left on the right side, and that's big G, the mass of the Earth, divided by the radius. Please note, this is not the radius of the Earth, right? This satellite is not on the surface of the Earth. It would be very messy if it was. This satellite is above the Earth, so this is a radius that's greater than the radius of the Earth. And you'll see that here as we plug in the numbers. Earth's radius was 6.38 times 10 to the 6th. Now we're 6.58, because 200 kilometers comes out to be 2 times 10 to the 5th meters, or 0.2 times 10 to the 6th And that's what we needed added, right? 6.38 becomes 6.58 when we add 0.2. Anyway, when we plug those numbers in, mass of the Earth has not changed, big G has not changed. We discover the velocity truly is very, very large, 7.8 times 10 to the 3rd meters per second, or almost 8,000 meters every second. Well, remember, 1,000 meters is a kilometer. So we're talking about 8 kilometers a second, and maybe that's still not meaningful to you because you live in America and you think in terms of miles. So 8 kilometers is roughly 5 miles. So if you could go 5 miles a second, 5 miles a second, that's really, really, really fast. For some perspective, that's Edwardsville's about 15 miles from downtown St. Louis. So that's here to the arch in 3 seconds. 3 seconds. That's really, really, really fast. My in-laws live in Ohio, 500 miles away. So I could get to their house, which normally by car takes me 8 hours. I could get there in 100 seconds if I could travel at this speed. 100 seconds is less than 2 minutes. I mean, this is crazy, crazy fast. And of course, nothing down here near the surface can go this fast because the air resistance would quite literally cause you to burn up immediately. Like I get this question from my students, I'm like, does Superman throw a baseball fast enough to put it in orbit? Well, if he threw a baseball from down here at that speed, it would burn up before it went a mile because of the incredible air resistance. Even if he was capable of launching it from his hand with that speed initially, you would burn up, which is why we have such a challenge getting things back from space, right? When we send people up in space shuttles or in space capsules, their problem is they have to go this fast to stay in orbit. But when it's time to come down, they slow down a little bit, and then they again, when they slow down a little bit, they'll start spiraling in. Well, then they hit the atmosphere going maybe 4 miles a second, 3 miles a second, and that's still very, very fast, and it creates a lot of air resistance, which is good. That's what further slows them down, but it also creates an immense amount of heat, and if the spacecraft is not properly shielded from that heat, it can cause destruction and can destroy the space capsule, as happened to the Columbia space shuttle, and as they were worried was going to happen to Apollo 13, but turned out their heat shield had not been damaged, and so they were able to make it back safely. So you got to go really, really fast to be in orbit. So that leads us to a second question, which is how long does it take you to go around the Earth if you're going that incredibly fast? So how long does it take a satellite to go around the Earth? This would be, again, anything in low Earth orbit. The space shuttles used to go up to low Earth orbit. The space station is in low Earth orbit. A number of our satellites are in low Earth orbit. So how long does it take them to go around? So distance is equal to velocity times time. That's all the way back from chapter 4, from the very beginning of physics. So if we want time, we take our distance divided by our velocity. In this case, the distance to go around a circle is called the circumference of the circle, and we can express that in terms of the radius, which we have. So our circumference divided by our velocity, 2 pi r divided by our velocity, 2 pi times this radius of our satellite from the center of the Earth divided by our velocity, which was 7.8 thousand meters per second, yields 5,300 seconds, which if you divide by 60 comes out to be 88 minutes. So those satellites in low Earth orbit go around the world every 88 minutes. So it's one of the jokes the astronauts tell on the International Space Station. You know, if you're getting homesick, just wait an hour and a half. You'll be sure to come over North America, and you'll be able to see your home, even if you can't go there very directly. But that's how quickly these low Earth orbit satellites go around. So now we need to address one further item, which we can now address because of the physics we understand. Why do the astronauts float? What does it mean to be weightless? Or what does weightlessness mean? And is this the same as zero gravity, zero G? What's going on? So again, there's a video. Involves an explanation, but also involves interviewing people and asking them why do the astronauts float, and what most people on the street think versus what the actual answer is. So you can pause and watch that video now, and then I'll give my explanation. But you can see this person, she's clearly floating in the space station, and there's no wires, there's no trick photography. This is what's actually happening up there. But the question is, why? Why does she float? If we'd stuck a scale underneath her, she wouldn't even touch the scale, so the scale would read 0. So she wouldn't have any weight. So why is that? So if we think of the simple definition of weight, right, force gravity equals mg, and this is, you know, not the full equation, but it would come out the same as the full equation. The reality is, when you're 100 or 200 kilometers up, your little g is still 9.7. I mean, it doesn't get very much smaller, really, at all. So weight is force of gravity. We say weight is equal to force of gravity, and force of gravity is mg. There's only two parts to the equation. We know the mass can't be 0. We know she's not massless. The mass is the stuff that makes us up. We still have that stuff. So if the mass can't be 0, then there's only one other thing in the equation. So does that mean that g's got to be 0 if you're in orbit? And that's where this idea has come from, and it's a very wrong idea, but it's somebody looking at this equation and using their logic to say, well, I know she hasn't disappeared. She still has mass. So the only other solution is that gravity must not be working on her anymore. But that falls apart real quick, right? Because we just got done talking about the fact that the moon goes in a circle and the space shuttle goes in a circle, and they both go in a circle because something's pulling them toward the center. And that something pulling them toward the center is gravity. So if gravity's pulling on the space station, if gravity's pulling on the moon, pull them toward the center to make them go in a circle, does it make sense that somebody inside that spaceship is somehow free from gravity? Doesn't really make sense. So how do we explain this? How does this work out? Well, the question actually comes back to this equal sign. Weight is not actually the force of gravity on you. Weight is actually, when you stand on a scale, the weight that is measured is actually how hard the scale is pushing back on you. It's actually your normal force. And again, I can best explain that by saying, you know, if someone comes along when you're standing on the scale and they put their hands on your shoulders and push down, the scale reads more. Or if they grab your belt and pull up, the scale reads less. And obviously, the force of gravity pulling on your mass is not changing because somebody's got their hands on your shoulders. Your force of gravity is not changing, but what the scale reads, which we call the weight, is changing. And that's because the normal force is adjusting because there are other vertical forces present, and so the normal force is going to adjust to cancel out all the other vertical forces. So on Earth, when we stand on a scale by ourselves, you know, this is true. Our weight force, which is our normal force, is actually the same as our gravity force. And that's why we get into this way of thinking and why we write this equal sign. But what's going on in orbit is because the spaceship is falling, right? Go back to our discussion of the cannonball. The cannonball is falling around the Earth. So the space shuttle, Sputnik, the moon, all these things are falling around the Earth. They're falling. They're falling. They never reach the Earth, but they are always falling toward the Earth. And because they are falling, and because the person is inside that ship and they are falling too, right? Normally, when we see something falling, we can see the background moving, and so we know that they're falling, and we don't have much thought about what do they weigh while they're falling, because we know that they're moving, right? We can think of gravity as being an acceleration, right? F equals ma. So when something's falling, it's like, well, yeah, there's nothing supporting them. Gravity's making them fall. They're accelerating downward. But we don't think as much in terms of their weight at that point because they're being accelerated by gravity. But they are falling inside of the ship. So the ship is falling around them and they are falling inside the ship. And that's why they never get any closer to the ground. That's why they don't press on the scale, because the scale is falling just as fast as they are. They're never going to reach the scale. They don't feel like they're falling. They're falling around a very large Earth. And they're falling in a context where everything else is falling too, so they don't feel the fall, but they are floating. The same thing would happen to you if you were in an elevator in a tall building and the elevator cable snapped. You would be falling inside of a container that was falling, and you would effectively float on the way down. At the bottom, you'd have issues, but you would be floating on the way down. They never catch the floor because the floor is always falling around the earth, and they're always falling around the earth. And because they never catch the floor, there's no normal force, and therefore there's no weight. So just to drive home the idea that when you're falling, you don't have any weight, we have this simple in-lab experiment, right? This is a spring scale. It stretches instead of compresses, but it's the same idea. We have a 0.5 kilogram. It's hanging on the spring scale. The spring scale reads 4.9. It's exactly what we'd expect. 0.5 times 9.8 would give us 4.9. You can clearly see as long as he's holding the scale, it's going to read 4.9, but he drops the scale, and they took a really good sharp picture, in motion picture, and you can see that the scale is now reading 0 while the object is falling. So while it's falling, it has no weight. And if you were, inside that yellow mass, you would be floating. And again, we do this on the Earth. We do this on the Earth to train our astronauts. We take them inside of an airplane. We fly the airplane very high in the sky, and then the airplane basically goes into a dive. And while the airplane is diving, it is falling, and the people inside of it are falling, and you get a few seconds worth of, maybe minutes worth of weightlessness, depending on how high they fly. But then the pilot has to pull out at the bottom so that you don't hit the ground and have bad results. But that's how we train our astronauts to get used to the feeling of weightlessness, the feeling of floating. But 0G is really a bad way to describe it. Even weightlessness is not the best way to describe it. I don't have a better way to describe it. I'm just saying both of those are limited because of our understanding of what weight normally means on Earth. That phrase can be confusing, and 0G is just plain not accurate. There is not a 0G. You would have to, humans have never experienced 0G. You would have to go an incredibly long ways away from the Earth to experience no G's from the Earth. And yes, well, when the astronauts went to the moon, then they were experiencing G's from the moon instead of from the Earth, but they were still experiencing G's from something. Being totally free of gravitational pull would require exiting the solar system, which we have not done. So that is almost the end of our presentation, and we're going to talk about satellites and the different types of satellites very briefly here, and then we will be done. So we have 3 different types of orbits described here. We have the geosynchronous, which again, geo means Earth, and synchronous means synchronized. So it's synchronized with the Earth. These satellites are not going in perfect circles. They are typically going in a very elliptical, very oblong shaped orbit that will keep them above the same part of the Earth all of the time, so that they are synchronized with the Earth. So instead of an 88-minute orbit, they have a 24-hour orbit so that they stay above the same part of the Earth, and so you can point your satellite dish at them and always communicate with them. So satellite radio, satellite TV, those sorts of things need geosynchronous orbits. Asynchronous simply means it's not synchronized with anything. These are the ones in low Earth orbit, in circular low Earth orbit, going around every 88 or 90 or 95 minutes. Spy satellites can then fly over whatever part of the world we're trying to study every hour and a half and take new pictures. The GPS satellites, there's just a whole series of them going around the Earth in different orbits at 90 minutes. If you've ever had your GPS, either when you first turn it on or whether you're coming out of a parking garage or something that says it's searching for satellites, it needs to hit 4 different satellites, and with 4 different satellites, it can confirm exactly where you are on the Earth in 3 dimensions, and that's how it does it. But it's got to find those satellites, and they're orbiting the Earth in a bunch of different asynchronous orbits. And then you have the polar orbits where it goes over the North and South Pole, which is really convenient because then you have the whole planet rotating underneath you, and you can work on mapping the whole planet, whether you're trying to map heat signatures or light signatures, or maybe you've got a really sophisticated radar system that's measuring the topography of the planet. We have a number of these around other planets that are trying to map, say orbiting Mars in a polar orbit or Venus in a polar orbit, and trying to map the planet in that way. Because as the planet turns and you go around, eventually you will be above every single point on the planet if you do it long enough, and so you'll get a complete map. So those are the different types of orbits that we put our artificial satellites in. I hope this presentation has made sense, and this is the end of chapter 9.